The ribosome is an important target for many different types of antibiotics. Protein synthesis inhibitors, specifically erythromycin and telithromycin, block the transfer of tRNA molecules between the A site and P site of a bacterial ribosome. This halts the growth of polypeptide chains, preventing the biological process of translation. The structures of erythromycin and telithromycin are an excellent case study in drug design, as their similarities and differences have unique impacts on their ability to bind to this target. Erythromycin is a member of the Macrolide class of protein synthesis inhibitors. Telithromycin is similar, but contains a ketone group in place of the cladano sugar on erythromycin. Telithromycin is considered a ketolide for this reason. In terms of design, both drugs share common structures. They are both characterized by a large lactone-containing ring consisting of 14 carbons, as well as a disosamine sugar important for binding to an adenine RNA nucleotide within the active site. As mentioned before, erythromycin contains a cladano sugar not present on telithromycin. Erythromycin only participates in one hydrogen bond in the active site, between an oxygen on its disosamine ring and a nitrogen on an adenine nucleotide in the active site. The cladano sugar does not participate in any appreciable bonding. A simplified 3D representation of the active site shows the close proximity of the oxygen and nitrogen moieties in question. The main difference with telithromycin is that it contains an alkyl-aryl side chain that branches from 2 carbons on the lactone ring. This side chain participates in a strong hydrogen bonding interaction with the cytosine RNA nucleotide in the active site. The interaction between the disosamine sugar on the drug and the adenine nucleotide in the active site is preserved in telithromycin as well. Note that the alkyl-aryl side chain is planar in 3D space, which facilitates pi stacking interactions with the cytosine nucleotide, colored in pink. This additional interaction allows for a 10-fold increase in telithromycin's binding affinity over erythromycin. This illustration summarizes the relevant interactions of the two antibiotics within the active site. Both antibiotics participate in hydrogen bonding with the adenine nucleotide, but only telithromycin has additional interactions with the cytosine nucleotide via its alkyl-aryl extension. Resistance can develop to these antibiotics through multiple mechanisms, but a specific route of resistance involves the mutation of key RNA nucleotides within the macrolide active site. Mutations can lead to changes in the binding affinity of these antibiotics. One important observed mutation involves the substitution of the aforementioned adenine nucleotide to guanine. Guanine contains an amine group shifted relative to adenine, bringing the nucleotide in closer proximity to the drug. Artificially mutating the nucleotide in question illustrates the steric clash that occurs between the nucleotide and the drug when switching between adenine and guanine. In reality, the antibiotics can compensate for this by slightly shifting their position in the active site, though this results in a 10,000-fold decrease in binding affinity.